Yield and defectivity in semiconductor industry. Welcome to this session on yield and defectivity in the semiconductor industry. Yield and defectivity are fundamental concepts that determine success in manufacturing. Yield measures how many functional chips are produced from a wafer, and defectivity tracks the presence of unwanted particles, process issues, or material flaws. Together, these factors impact three major pillars. First, manufacturing excellence. High yield and low defectivity indicate a well-controlled process that consistently meets design specifications. Second, quality control. Monitoring defectivity ensures that chips function reliably, which is crucial for end-user performance and safety. Third, economic impact. Yield losses translate to lost revenue and higher production costs, while defect reduction strategies help increase profitability. This presentation will guide you through the essential principles and practical insights to help you understand and manage these critical parameters in semiconductor production. What are semiconductors? Semiconductors are the essential materials at the heart of modern electronics. What makes them unique is their ability to control electrical current. Unlike conductors like copper, which freely transmit electricity, and insulators like rubber, which completely block it, semiconductors sit in between. Their electrical behavior can be precisely tuned through a process called doping, allowing them to act as switches or amplifiers in circuits. This property makes them critical in building electronic devices. Semiconductors power smartphones by enabling processors, memory chips, and sensors. In computers, they form the core of CPUs, GPUs, and RAM. In the automotive industry, they are used in engine control units and safety systems. In the medical field, semiconductors support life-saving devices like pacemakers and imaging tools. And in the growing world of IoT, they drive smart homes, wearables, and connected devices across industries. Manufacturing. From sand to chips. The process of manufacturing semiconductors begins with silicon, which is refined from sand to produce ultra-pure silicon wafers. These wafers form the foundation upon which all chips are built. Next is fabrication, the heart of semiconductor manufacturing. This stage involves hundreds of intricate steps, including deposition, lithography, etching, doping, and more, all aimed at building tiny transistors and wiring structures layer by layer. Once fabrication is complete, the wafers move to the testing phase. Here, quality verification is conducted to ensure that each chip meets performance specifications. Only then are functional chips packaged and finalized for use in electronic devices. However, not every chip manufactured functions perfectly. That's the key challenge. This is where the concepts of yield and defectivity become critical. Yield tracks how many good chips are produced, while defectivity explains why some chips fail. Both are essential to improving manufacturing performance. Understanding yield. Yield is a fundamental metric in semiconductor manufacturing that measures efficiency and effectiveness. It is defined as the number of working chips divided by the total possible chips on a wafer. In simpler terms, yield tells us the percentage of chips that function correctly after production. For example, if a wafer can produce 100 chips and 70 of them work as intended, the yield is 70%. This level is generally considered a good yield in many fabrication processes. A higher yield means better manufacturing efficiency, less waste, and greater profitability. It also indicates that the production process is well controlled, with fewer defects and issues affecting performance. Yield is a key driver of cost efficiency. Boosting it means more usable chips from the same resources. Ultimately, understanding and improving yield is essential to staying competitive in the semiconductor industry. Understanding yield. Definition and types. Yield in semiconductor manufacturing can be broken down into 4 key types, each representing a different stage in the production process. First, we have wafer yield, which typically exceeds 95%. This measures the percentage of wafers that complete fabrication without breaking or suffering major damage. It acts as the first checkpoint for process stability. Next is die yield, ranging from 60 to 80%, and it's often the most critical yield metric. It refers to the proportion of individual chips, also called dies, on a wafer that pass initial electrical testing. Then comes probe yield, which falls between 70 and 85%. This measures the success rate of dies passing electrical tests while still on the wafer, offering early defect detection. Finally, final test yield, typically above 90%, assesses packaged chips that pass thorough, post-assembly testing. Each yield type plays a vital role in quality control and overall manufacturing performance. Understanding yield. Yield in semiconductor manufacturing represents the percentage of good units produced compared to the total number of units started. It is measured at multiple stages throughout the manufacturing process, beginning with fabrication. At this stage, we calculate wafer yield, which reflects how many functional dies are present on a wafer after production. The next checkpoint is the probe test, where die and probe yield are evaluated. This step verifies which dies function correctly before packaging. After passing this test, the dies are sent for assembly and packaging, where physical damage or contamination could still occur. Finally, the packaged chips undergo a final test, leading to the calculation of final test yield. A key insight to remember is that overall yield is the product of wafer yield, die yield, and final test yield. Each stage plays a critical role in maintaining high overall manufacturing efficiency. Understanding defectivity. Defectivity refers to unwanted imperfections in semiconductor manufacturing that lead to chip failures. These defects can drastically reduce yield and reliability. A defect is any deviation from the intended structure, and common examples include particles, pattern misalignment, or electrical faults. Defect density, or DD, is calculated using the formula total defects divided by wafer area, typically expressed in defects per square centimeter. The usual defect density for production processes falls between 0.1 to 0.5 defects/cm2. Among all defect sources, particles are the most common, accounting for 40%. These include dust or debris settling on wafer surfaces. Lithography contributes 25%, often due to pattern misalignment or exposure issues. Etching defects make up 15%, involving incomplete or over-etching during material removal. Electrical defects at 12% arise from short circuits or open connections. Lastly, 8% come from variations in process parameters that breach control limits. Understanding defectivity, impact, and importance. Defect density has a direct and measurable impact on manufacturing yield. At a defect density of 0.1 defects per square centimeter, the process is considered excellent and can result in yields as high as 85%. When defect density rises to 0.3 defects per square centimeter, yield drops to about 70%, which is still acceptable but requires close monitoring. At 0.5 defects per square centimeter, the yield drops further to just 50%, indicating a process that needs significant improvement. These yield percentages show how even small increases in defect levels can cause substantial yield losses. That's why defectivity matters. First, there's a major cost impact. Each defective chip results in lost revenue. Second, lower yields delay the time to market by slowing production and increasing rework. Lastly, competitiveness is affected, as higher yields lead to lower production costs and more competitive chip pricing. Improving yield from 70% to 80% can save millions per fab annually. Measurement and monitoring. To ensure high yields and product reliability, semiconductor fabs rely on advanced measurement and monitoring systems to detect and track defects. Optical inspection uses high-resolution cameras to scan wafer surfaces, offering a 95% detection rate. It excels at identifying surface particles and pattern defects quickly and efficiently. For even higher resolution, E-beam inspection is used, with a 99% detection rate. This method uses an electron beam to detect subsurface defects at the nanometer scale, including issues in critical layers. Electrical testing offers 100% coverage and involves probe tests that verify the electrical functionality of each die. These tests provide performance checks and go/no-go decisions. In addition, inline monitoring operates 24/7 in real time. It continuously measures key process parameters such as temperature, pressure, and chemical levels to detect deviations. Together, these tools provide a comprehensive approach to maintaining process integrity and minimizing defectivity. Real-time yield monitoring system. Modern fabs rely on real-time yield monitoring systems to quickly detect, analyze, and respond to process issues. The system starts with data collection, where multiple sensors across the equipment and process stages capture defect-related data. This step ensures rapid detection, typically in less than 1 minute. The captured data is then fed into AI analysis engines that perform pattern recognition and classification, offering an impressive 99.9% accuracy. Next, the analyzed results are displayed in a centralized dashboard. This dashboard provides real-time yield metrics and alerts for immediate awareness. It enables continuous 24/7 monitoring and helps engineers make data-driven decisions. Finally, process control takes over by making automatic adjustments to correct deviations. This results in up to 10 times faster response compared to manual methods. Altogether, this smart, integrated system significantly improves production efficiency, reduces waste, and enhances both yield and product quality. Measurement and monitoring. Measurement and monitoring are essential for detecting and tracking defects throughout the semiconductor manufacturing process. Early detection allows defects to be identified before they spread to multiple wafers. This proactive approach can help save 50 to 80% of potential yield losses, minimizing the risk of widespread damage and costly rework. Predictive analytics further enhances our capabilities by forecasting yield issues 3 to 5 days in advance. By using historical and real-time data trends, these models can predict failure points or anomalies before they happen, enabling teams to take corrective action ahead of time. Finally, automated response systems take this to the next level. These systems make real-time adjustments to the process without human intervention, responding within seconds. This ultra-fast response helps maintain process stability, reduce downtime, and improve overall manufacturing efficiency by minimizing human error and maximizing uptime. Yield improvement strategies. Boosting manufacturing yield requires a combination of proven strategies designed to reduce variability, eliminate defects, and optimize performance. Process control contributes to a 15% yield gain by maintaining tight parameters, keeping temperature within plus or minus 0.1 degrees Celsius, pressure within plus or minus 0.01%, and chemistry within plus or minus 0.5%. This ensures uniformity and prevents process drift. Defect elimination adds another 20% yield gain through robust root cause analysis, strict contamination control, and consistent equipment maintenance. These efforts target the underlying issues that cause defects, preventing their recurrence. Statistical control contributes a 10% yield gain by leveraging control charts, monitoring process capability indices like CPK, and analyzing trends over time. These tools enable teams to track stability and spot early signs of variation. Finally, AI analytics provides the highest impact, with a 25% yield gain. Using predictive models, pattern recognition, and optimization algorithms, AI identifies complex relationships and prescribes data-driven actions for continuous improvement. Continuous improvement cycle. A strong yield improvement strategy is grounded in the continuous improvement cycle driven by the PDCA methodology: plan, do, check, act. This structured approach starts with planning for improvement opportunities, executing them on a small scale, checking the results, and then acting to standardize successful changes. The process begins with data analysis, where teams identify recurring patterns and root causes of yield loss. This step is essential for understanding where problems originate and what factors are driving defects. The next phase is optimization, where targeted improvements are implemented to eliminate waste, reduce variation, or enhance process efficiency. This leads to results, achieving higher yield and improved product quality. Supporting elements include clean room environments for particle-free manufacturing, preventive maintenance to reduce downtime, DFM or design for manufacturability to minimize defects, operator training for fewer errors, quality control gates for better defect detection, and supplier engagement to ensure high-quality, cost-effective materials. Yield improvement outcomes. Effective yield improvement strategies can deliver substantial business impact across key performance areas. Yield can be increased from 70% to 90%, representing a major boost in manufacturing efficiency and product output. This translates directly into financial benefits, with potential annual savings of $50 million. These savings come from reduced rework, fewer scrap wafers, and improved throughput. The good news is that the typical implementation time for such yield enhancement initiatives is just 6 months. This short timeline allows organizations to realize gains quickly and begin reinvesting in other areas. Perhaps most compelling is the return on investment, which can reach as high as 500%. This level of ROI underscores the value of combining data-driven decision-making, process optimization, and continuous improvement practices. For both mature fabs and new production lines, these strategies are not just operational upgrades, they are strategic levers for growth and competitiveness. Industry challenges and trends. The modern semiconductor manufacturing landscape is shaped by increasing complexity and urgency. Shrinking nodes are now pushing the boundaries of technology at the 3 nanometer scale. At this level, quantum effects become significant, requiring extreme ultraviolet, EUV, lithography, and atomic-level precision. The complexity level is extreme, making process control and defect prevention more critical than ever. Rising costs further intensify the challenge. A new fabrication facility now demands an investment of around $20 billion. Equipment can cost 10 times more than previous generations, and mask sets alone can exceed $50 million, with development timelines stretching beyond 5 years. Defect detection is also more difficult, with feature sizes shrinking below 5 nanometers. Manufacturers must now detect sub-wavelength defects, navigate 3D structures, and mitigate multi-layer interference. At the same time, there are increasing speed demands, bringing products to market in just 6 months. This requires faster ramp-ups, quicker yields, and compressed design cycles. Future outlook and conclusions. The semiconductor industry is heading toward a bold future, projected to reach a $1 trillion market value by 2030. To achieve this, companies are targeting a 95% yield, which requires precision, innovation, and relentless focus on improvement. A 50% reduction in manufacturing costs will be necessary to stay competitive, especially as complexity increases. Full adoption of AI, 100% integration, is expected to drive this shift by enabling smarter process control, defect prediction, and optimization. Payback periods for new investments are expected to shrink to just 6 months, a timeline that demands agile deployment and rapid ROI. Looking ahead, the next frontier is 1 nanometer technology, where atomic-scale engineering becomes the norm. To succeed, the industry must commit to excellence through continuous improvement, embrace innovation to lead technology forward, and define success by measurable yield and profitability. Mastering yield and defectivity truly means mastering the future of semiconductors. Industry challenges and trends. In the modern semiconductor manufacturing landscape, innovation is accelerating through transformative technologies. One key trend is the use of AI and machine learning analytics to enable real-time yield prediction, achieving up to 90% accuracy. These models help manufacturers detect process deviations early, significantly reducing scrap and improving efficiency. Advanced inspection techniques, particularly with multi-beam E-beam systems, are now 100 times faster, drastically increasing the throughput for defect detection. In-situ monitoring offers real-time process feedback with a response time of less than 1 second, allowing immediate corrections and tighter process control. Digital twins, or virtual fab simulations, are revolutionizing factory operations by offering up to 50% cost reduction through predictive modeling and scenario planning. Finally, quantum computing brings an exponential leap in processing capability, providing 1,000 times more compute power, enabling complex optimization algorithms that were previously impossible, and pushing the boundaries of semiconductor design and manufacturing efficiency. Industry challenges and trends. Semiconductor manufacturing is undergoing rapid transformation, but it's also facing intense market pressures. The slowing of Moore's law presents a critical challenge, making it harder to achieve performance gains through traditional scaling. Competition remains high, forcing companies to innovate faster while meeting extreme customer expectations for quality, performance, and delivery. Investment requirements are massive, with fabs costing tens of billions of dollars. To navigate these pressures, AI-driven solutions are becoming vital. AI technologies can predict, detect, analyze, and optimize manufacturing processes, resulting in a 30% improvement in yield. Looking forward, between 2025 and 2027, AI is expected to become standard across all fabs. From 2028 to 2030, fabs aim to achieve fully autonomous yield management. By 2030 and beyond, quantum-enhanced optimization may redefine process control. With a $600 billion market size in 2024 and 20% annual growth, the industry is projected to reach $1 trillion by 2030, with 85% AI adoption by 2026 and a 1 nanometer technology node on the horizon. Economic impact and cost analysis. Yield and defectivity have direct and dramatic financial implications in semiconductor manufacturing. A 1% drop in yield can lead to a staggering $2.5 million in lost revenue. This loss stems from reduced revenue per wafer, increased cost per die, and underutilized fab capacity. On top of that, each critical defect can cost approximately $50,000. These costs arise from extended inspection time, rework, and the need to scrap valuable materials, impacting both productivity and profit margins. Building and operating a leading-edge fab requires a massive $20 billion investment, including $15 billion for equipment, $3 billion for the facility, and $2 billion in R&D. However, these high costs can be justified by impressive returns. A modest 5% improvement in yield from a $10 million investment can generate $40 million in annual savings, delivering a 400% return on investment. This highlights the immense value of precision, innovation, and defect control in modern fabs. Economic impact and cost analysis. Improving yield has a powerful effect on semiconductor revenue. A 10% increase in yield can drive an additional $125 million in revenue, demonstrating the steep value curve of even small yield enhancements. As yield rises from 60% to 90%, revenue growth accelerates non-linearly. In terms of manufacturing cost, yield-related losses represent a significant burden, accounting for 35% of total production costs. This includes lost value from defective wafers and the inefficiencies in rework and scrap. Other major cost components include materials, equipment, labor, and overhead. Understanding and managing these areas is key to profitability. On the investment side, the return on yield improvement initiatives becomes evident over time. The ROI timeline shows initial quarters in the red, but by the 6th quarter, gains soar to over 400%. The typical payback period is just 18 months, emphasizing that strategic yield improvements not only enhance revenue, but also generate rapid and substantial returns. Economic impact and cost analysis. Improving semiconductor yield impacts nearly every aspect of manufacturing economics. The cost per die drops dramatically, from $75 at 60% yield to just $45 at 85% yield. This efficiency also boosts wafer value, with high-yield wafers worth $8,500 compared to $3,200 for low-yield ones. Margins improve significantly as well. A 5% gain in yield can increase gross margin by 15%. Time to market is crucial. A single day of delay in launching a product can result in a $2 million loss, underscoring the urgency of efficient production. Higher yields also translate into a competitive edge, with a 5% gain in market share. Risk is also better managed, with yield control reducing operational risks by up to 80%. With a typical yield program investment of $100 million, companies can realize $500 million in annual savings. The ROI ratio is an impressive 5.1, with programs showing an 85% success rate and achieving break-even in as little as 6 months.